Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today we're very happy to have Sami Zahir visiting us. So Sami is a grad student at the University of Virginia, finishing up very soon, working with David Evans, and he's been working on building one of the state-of-the-art multi-party computation libraries, among other things. And I'll let him tell us more about it.
Thanks. I'm Sami. I previously interned here with Brian Parno. I was working on verifiable computation. But yeah, as Melissa said, we'll be talking about the rest of my work back in University of Virginia. Most of it is on multi-party computation. To give you a brief overview, in case you're not familiar, is the idea is that, let's say today, if I meet somebody and I want to see if we know other people, if we have common acquaintances, what do we do? So on Facebook, let's say Facebook has all our friend lists, and they will say that, okay, these are the friends in common, right? We have a trusted third party who takes all our data and then does the comparison. The idea is that we shouldn't have to do that. So if you and I have our own private information, let's say our friend list or let's say genetic information, and we want to see how closely related we are, we should be able to do that computation without having to reveal our data either to the trusted third party or to each other. We should be able to perform computation directly on private data. So that's the premise of secure multi-party computation, is that we don't have to reveal anything other than just the output. Okay? So the other applications could include secure auctions, any other data analysis algorithms, neural network algorithms, and whatnot. So now there are ways of computing on private data directly, and computing arbitrary functions on private data. And the way they generally work is by using Boolean circuits. So there are protocols that will take any Boolean logic circuit, AND gate, OR gate, and whatnot, and glue them together, and finally give you a protocol that will execute that circuit. So some of the input wires will be from one party, some of the input wires will have data from the other party, and then you execute the entire circuit, and finally the output can be shared between several parties, between the parties you want. Which is great, but it makes it kind of hard to use for everyday programmers. So my research goal has been so far to make it easy for normal programmers to use. So if somebody wants to use these protocols now, they will either have to be experts in cryptography or experts in circuit design, which turns out to be non-trivial, even though digital logic design is an undergrad course in pretty much every computer science curriculum. So what we want to do is sort of give programmers the tools necessary so that they can use these sort of technologies without being experts in cryptography. Some of that has been in the form of a new language with its own compiler. So it's a language that I developed. It was mostly C-like language with a few extra annotations and keywords. So for instance, you could have variables declared as obliv, which are sort of secret variables, which will be any computation done on them will be done cryptographically. Then you would say that, okay, certain variables come from party 1, certain variables come from party 2, and then finally reveal the values to both parties. So you do that, and finally you get the whole program, you compile it, and you get the protocol, and they execute it. So the programmer that writing this kind of code will not need to know anything about what's going on underneath. Okay? Now, if you look at what's going on around it in order to make it all work, you have the Oblivious framework in the middle, but then some of my research has been both in the front end and the back end side. So for instance, it turns out that certain algorithms which are fast in normal computation are not necessarily fast in MPC and vice versa. So we had to come up with data structures and algorithms that is actually fast in MPC and make that available as normal functions to programmers. And on the other hand, in the very back end, we had to come up with ways of reducing bandwidth usage, reducing CPU usage, and whatnot for the actual cryptographic primitives. So that's been sort of the outline of my research so far. In this talk, we'll be mostly talking about this side of the equation. So we'll be talking about how we can do data access fast inside MPC. So the central question would be, if you have a situation such as this, where you have some memory access in a program, and you want to run this program in MPC, and whenever you have an array access, you're accessing location J, and let's say somehow this J variable is dependent on secret data, the data that you want to keep secret. So you cannot just reveal that I'm accessing location J, because that will reveal some intermediate results that you want to keep secret. The idea was that we'll only we'll have inputs that are private. The only thing that will be revealed is the final output. The intermediate results should not be revealed. Do you have a question?
Yeah, I did.
Yeah.
Sorry, I did. I'm sort of lost. Like, where is this computation happening? Is it happening in one of the two parties? Or
great. So it's happening. It's a distributed computation.
Okay.
So say if you and I are the two parties, our machines will be communicating with each other and run some cryptographic operations such that the protocol, the computation happens in a distributed fashion. We will both do some computation, but such that the intermediate values are not revealed to either
Okay, so
parties.
what is being shown here is just a specification of the computation.
Yes, yes, yeah, absolutely. So yes, and feel free to ask questions, by the way. It's perfectly fine that if we go off into a tangent that you're more interested in, and I don't get to cover, that's perfectly fine, and much rather cover something that you guys are more interested in. So yeah, something as simple as array access is actually difficult if you want to hide which location you're accessing, right? The simplest way to do it would be, let's say, even if you're accessing just one element, access all of them. Like if you scan through the entire array just to hide which element you're actually interested in. That would be the naive linear scan approach. But you've just taken an operation that was constant time and expanded out to a linear time operation. Most programs would become unbearably slow, regardless of the fact that MPC is already slow. So it's not going to work. So if you want this technology to be used, programs that are easy to write should remain easy to write. If we have to completely rewrite programs, that's a problem. So the way to solve it, there are essentially two different approaches, right? One would be to transform the program or come up with algorithms such that your program is accessing memory locations in a very deterministic fashion, independent of your input data. If you can express your program in that fashion, then great. Your array location is no longer revealing private information. The other approach is to randomize it. You shuffle the data around constantly, such that even if you reveal which location you're accessing, that's perfectly fine, because that does not really necessarily correspond to the logical identity of the element, and that might still protect your information. So that gives you an outline of the two halves of my talk here, okay? The first half would be to come up with algorithms which are basically circuit structures that will that will give you a schedule by which you can access data in a particular deterministic fashion, independent of input data. Those are pure circuits, but they only work for special cases. In the general case, it's not possible. If you have completely general random access, I can't help you there. But they're faster. On the other hand, you have the general random access, where you keep shuffling the data. It will hide any kind of random access. It will work all the time. But the problem is, it is definitely much slower. You have to do some extra operations there. So yeah, before I get started on the first half, questions? Yes?
Yeah, just on the basic model, so should I think of this array as being the input of one of the parties? Or
No.
is this sort of something that's
Some intermediate
distributed
results.
between two of them?
Distributed between two.
Roughly?
Yeah. Yeah.
Okay.
It could be an input, that's fine. Any question?
Yeah.
Okay, great. So circuit structures. So in this part of talk, we'll be actually covering the very basic data structures, so stacks and queues and associated maps. They are extremely easy to implement in normal programs. But the problem is, if you have a stack, and let's say you're pushing elements into it, if some condition, stack.push x, if your condition is secret, then the length of your stack becomes a secret value. You cannot reveal it. And the moment that happens, you sort of have to now figure out how to implement a stack without revealing where you are there. So the way we sort of represent it inside a circuit would look kind of like this. So you have some conditional push circuit made out of logic gates. Your inputs will be the condition that's secret, that's some intermediate value, x, which is also secret, it's getting pushed in. You have the old stack elements coming in and the new stack elements going out. Okay? And now what I'll show you is how to efficiently implement this push operation. Okay? Now, what's a naive approach? Well, here's a really naive approach. We have the old elements, A0, A1, A2, and 3. We have the new elements, the primes, you have the conditions. And these boxes are basically multiplexers. They will choose one or the other depending on the condition. Okay? So if condition is 0, they will all choose, let's see, the right-hand side of their inputs and pass it on to the output. If the condition is 1, they'll take the left-hand side. So if the condition is 1, x gets passed into A0, everything gets shifted. If the condition is 0, x gets ignored, and the old values just pass right through. Which works. This is a valid circuit for doing conditional push operation. The problem is, of course, we are using a linear number of gates to implement a single push. That's the problem we're sort of trying to avoid. The way we solve it is as follows. It's really actually quite simple. The idea is that we break up this buffer into small pieces, and we put empty spaces in those buffers, so that when we're doing the shift operation, we don't shift everything. It's basically as simple as that. So we take this one row. In the next diagram, consider just the top row. That's just the one row of the previous diagram. So the moment we're doing a push operation, we start by making sure that we at least have 2 empty spaces, right? So we have 5 elements here, 10 elements, 20 elements in the next level, and 40 elements, so 2 powers of 2 times 5. So we do 2 push operations. We know they'll succeed. We'll only have to access only the first level, the level 0, and nothing else.
Sorry, what do you mean by these levels?
So the top line there, top row, that's one of these buffers. Okay? So what we have is that we've taken this buffer and divided it up into pieces. So that's level 0, that's level 1 buffer. Okay?
So you're storing it with a bunch more space added.
Yes, yeah. And we maintain invariance of how many spaces we keep at each level. So after 2 operations, we started with at least 2 empty spaces. So we know after 2 operations, it might be full, depending on your conditions. So after every 2 operations, we shift from level 0 to level 1. After every 4 operations, we'll shift from level 1 to level 2, and so on and so forth. If you do that and count up the costs, you'll notice that, let's do the counting right here. For each operation, we're accessing level 0, right? So let's say 5 units of cost. After every 2 operations, we're accessing level 1. Well, level 1 is twice as big. So each time you pay 10 units. But you are accessing it half the time. So 10 times half. So again, 5. Similarly, level 2 will be 4 times as big, but access for 1/4 the time. So at each level, you're sort of paying on average of 5 units of cost per access. You have logarithmic number of levels because the level sizes are increasing. If you have n elements, you have log n levels. So what happens at the end is for each access, on average, you're paying 5 times log n cost, essentially. Some constant time log n cost. So that's how you do stack push. And the reason we have 5 is that we start with at least 2 empty spaces. If you want to do pop operations, then you'll need at least 2 full spaces so that you can actually serve up new elements. And then you'll need 1 extra element just in case some of the conditions were false, and you need odd number of elements. Yes?
So the idea is if you're not actually pushing something in that first step, you would like put an empty space there?
Yeah.
So 9 might be empty if the condition was
right. 9 might be empty.
And then when you smush everything over to the right, then you're collapsing all that.
Actually, no. Whenever we do right, so if 9 is empty, next time we push, 7 will just go here.
And that's because you read the whole thing, so you can just...
Yeah, it's just linear scan. Yeah.
How do you deal with errors? Like you do a conditional push, and then you do a pop, and then at that point, the pop might return an error, or it might not return.
Yes, great question. So you can do anything you want. So you can have it such that the error would be a secret condition. So first of all, in most cases, we just recommend that you write the program in such a way that that doesn't happen. You maintain your invariance. That doesn't happen. You can definitely have some extra circuitry during a pop operation. It will check whether or not it's empty. If so, it will set a Boolean flag. But then again, whether or not you reveal that Boolean flag is up to you. It might be an oblivious Boolean flag that you only reveal at the very end. If something went wrong, I'm not going to reveal the result. That can be done. So that can be, depends on your preference. Yeah, yes.
So where does the right-hand side end? So do you have to upper bound this?
Yeah, it's if you know that you have a maximum of n elements in the stack at any time, then you can just have log n levels.
But you have to know that statically, right?
You have to know that statically. You have to know something statically always. So for instance, if you're doing n push operations, you know it will never exceed n.
Right.
So statically, you at least have to know how many operations you're doing, because I mean you don't have to. So let's put it this way: if your number of you always have to reveal how long your program is running. That's something you're not able to hide. So if you can either reveal how many operations you need, or you can do extra operations, that's up to you. Yeah. Anything else? No? Okay. So that's stack. Similarly, I'm not going to go into details, but you can do queues in a very similar way. You'll just have a cyclic extra arrows going between them. But the result is the same. So when you do the evaluation, we just compared with linear scan here because that's pretty much the only thing that competes. Yeah, so that's what you expect with log. There's no surprises here, except for the fact that it's small. We don't have a hidden giant big O cost. It's doable. It's really efficient. And the best part is it's completely circuit based. So it doesn't matter what protocol you're using. There are many different protocols with which you can instantiate it. There's YAWS, there's GMW, you can have semi-honest, you can have malicious, whatever. The same algorithm would work unchanged. You don't have, it's very protocol agnostic. And so yeah, it's good that way. And the thing is that once you have stacks and queues, you can do memory access for any kind of locality. So if you have an array here, and you're accessing at index I and index j, and you know that they will only be incremented or decremented in small increments or decrements, then you can just break it up into many different stacks and queues and use stacks and queue circuits to access them in log n time instead of using a general Oblivious RAM. That would be much more efficient to do it this way. Right? Makes sense? I see some frowny faces. Okay.
I just have a question.
Yes.
So there's like Oblivious data structures, which are based on, I guess, just normal ORM.
Mm-hmm, yeah.
How is this, would you say, more efficient than?
Yes, at least in my experience, yes. The reason is whenever you use ORMs, those are not general circuits in the sense that you have to sort of reveal which path you're reading from and whatnot. You introduce the extra round latencies, and so you'll need to have extra steps if you want to go to malicious security and whatnot. So they come into play, whereas this is pure circuit. Anything that's circuit, it'll just run, and there's no round trip latency, nothing like that. So yes.
Okay, I was one of the frowning faces. What's the precise condition of locality that lets you model an array as stacks and queues?
So the condition is that whenever you access a particular index, the next index that you access needs to be within some constant number of steps. So if your constant is really large, you'll pay more. Yeah. Okay, great. The other thing we have is completely unrelated is batched operation. If you do not have any locality, but let's say you're doing many writes in one go, or many reads in one go, then you can use oblivious sorting-based approaches to get log square n performance. But yeah, these are sort of the pure circuit-based structures. So the conclusion for the first half is that when your application is such that you do not need perfect random access, completely general random access, great. There are always specialized circuit structures that you can use. For stacks and queues, we have like 10x speed up. For the batched operation, we have, I don't remember, 8x or something. And they're completely protocol agnostic. They're more versatile. You can use it with any existing protocols. So yeah, that was the first half. Before I go into the second half, questions? No? Good. OK, so that was for specialized access patterns. Sometimes we can't do that. Sometimes you have completely general random access. In that case, you kind of have to fall back on Oblivious RAM. Now, there has been a lot of work in this. Most of the implementations today that use Oblivious RAM use tree-based Oblivious RAM. They were first introduced by Elaine Shi and others. So if you look at the literature, there are tons and tons of paper. People have been working on it for a long time. These are what other people have done. And they have been implementing hybrid protocols between YAO and ORM just to see how they integrate together and what their performance are, which is great. And most of them all of them have been tree-based implementations. But if you look at, let's look at some performance numbers. So without ORM, what's the performance number? Writing a single 32-bit integer, you'll need 32 logic gates. Great. If you know the location, you know exactly where they're located. Raw YAO performance, it's 1 million gates per second is actually a low number. Today you can get at least 3 or 4 on a gigabit per second. But let's go with order of magnitude. 1 million gates per second. Great. So write speed, you do the division, you'll get 31,000 writes per second. OK, if you know the location is not dependent on private data, right? If you have to hide access patterns, let's say you have 2/16 elements, so 65,000 elements, you will, wait, did I do the math wrong? I did the math wrong. You'll be doing around, this is half access per second. So you will be doing, you'll be doing around 2 seconds per access, right? So that's sort of the order of magnitude. If you're using complete linear scan, like no RAM whatsoever. Now let's compare this to, keeping in mind the error in the slide. Sorry about that. Let's compare this to previous work of ORM performance. So this is from CCS of last year. This was circuit ORM, minimizing the circuit size for each ORM access. That's sort of the best you can do for MPCs. As you can see, if you have 2 to the power 16 elements, per access time is around 1 second, right? So at this point, it is almost in the same order of magnitude as a linear scan. That's where the break-even point is. So if you have less than that, there is no point even using Oblivious RAM, because a plain linear scan of accessing every single element will be faster per axis. And this is not even taking into account the fact that you have to initialize Oblivious RAM first. Or like, if you have an Oblivious RAM structure, you at least have to touch each element once just to initialize the structure. So not even taking that into account. I guess the response to that is, OK, great. I mean, ORMs are asymptotically better. So if you go big enough, ORMs should still win out. Yes, ORMs should still win out. If you go, let's say, 2 to the power 18 or 2 to the 20, 2 to the 20 is like 1 million elements, which is OK. Yes, it will definitely win out. But think about what that means. It means that, let's say 2 to the power 20. For 1 million elements, per access, you have to spend around 2 seconds. If you have 1 million elements, just to initialize, that's just to write each element once, you need 2 times 1 million seconds. That's 2 million seconds. That's about, I think, 2 weeks, a little over 2 weeks, just to initialize. What happens is, if we want to provide this as a tool to people and say that, hey, you can use this to do arbitrary computation, but if you need random access, by the way, you need to wait 2 weeks just to initialize the data. It's hard to sort of sell MPC to people. So we sort of have this strange situation where, yes, ORMs will provide advantages only for applications so slow where even MPC wouldn't be used, or for smaller cases, ORMs are still not usable. So what happens is that for many cases, people just wouldn't use Oblivious RAMs at all. They just use plain linear scan, which is which created this weird stigma against Oblivious RAM that, hey, this is too slow, nobody wants to use this, which we don't want. So the goals here for our case is that we want to design an ORM which provides benefits at much smaller size, and it can be initialized quickly. We don't need to go through that for initialization. So those are the two goals here. So yeah, I will start now describing how this ORM works for just 4 elements. Any questions so far? The goal. Okay. So let's say we have just 4 elements. This is the Waksman network for shuffling. So if you have 4 elements, so these lines are the data wires, and we want to just shuffle them. This is just a Waksman network, which means if they either swap or leave the elements unchanged, or swap the elements. If I have secret control bits controlling them, 0 and 1 control bits, I can use them to permute these inputs into any given combinations. So if you need to permute 4 elements, you'll need 5 switches. Okay? So the cost of shuffling 4 elements would be around 5 units, or 5B, let's say. Cost could be CPU cost, could be network cost, whatever. 5 units for shuffling 4 elements. So here's how we can construct an ORM. So just 4 blocks, right? You come in on 4 pieces of data, you shuffle them. Once it's shuffled, now if you, and let's say there is to the side, there's some map that says, okay, element 1 went to position 3, and element 3 went to position 2, and whatnot. So there's a small, like, 2-bit map of little things. So once it's shuffled, if you're accessing a certain element, and you reveal the fact that you're accessing this position, that's fine, because it's been completely shuffled. You don't know which original element actually went there. So you can actually reveal that, hey, I'm accessing that element, and you'll be paying a cost of B. And that's it. The next time you access an element, you have to reveal, you kind of have to access 2 elements, the same element as before and some other element, because you don't want to reveal whether or not it's a repeated access. So now you're paying a cost of 2B. The next time, you pay a cost of 3B, because you access the same elements as the previous 2 ones and a new one. You can see where this is going. So what we're going to do is not go to 4B again, and just shuffle it again, and then keep going. So for we do 3 accesses, and then shuffle again. We do 3 accesses, and then shuffle again. 3 accesses, and shuffle again. So every 3 accesses, we are paying a cost of 5B plus B, 2B, 3B, total of 11B. Which is kind of interesting. If you compare it with the linear scan would pay a cost of 4B per access, 12 by 3, whereas we are paying 11B by 3. So just at 4 blocks, we are already doing better than linear scan, which is much better than the previous schemes that we saw, right? And there is no extra initialization other than this shuffling, which is already.
If you do the 4th one before shuffling,
yes,
you'd also win.
You'd also win, but then instead of paying, your cost would be 15 by 4. So this is better. Yeah.
Also, how do you account for the cost of finding which one to access?
So you just have a small bit vector, which is a 2-bit value for each position, which is constant, independent of block size. So yeah.
Swept under the rug, assuming
it's kind of swept under the rug, yes. So the idea is that if you have a large enough block, that wouldn't matter. In practice, if you are accounting for, I don't know, we'll have the graph, but if you're accounting for, say, network bandwidth, block size of 36 bytes is good enough. So if you have larger than that, you can always just divide it up into larger blocks and use that. Yes. Yes?
So if you have a multiparty computation where the data is just like bits or something like that,
yes,
and you're just accessing a bit here and a bit over here, does that end up?
That may be too expensive, simply because of the metadata, like he said. Yeah, exactly. So what I would recommend in that case is to divide it up into several bits and then do a linear scan on each of them. No. Blocks of several bits. Yeah.
Is that better even if you're?
Yeah. Better
if
than
you're
what?
just accessing one bit
Yes.
at a time in like totally different places?
Yes. So, so the 2 alternatives you're proposing is that one would be scan all bits, and the other would be divided into 4 blocks and scan linear scan between just each of them. right? So yes, that will still win out. Yes, definitely. So yeah, that's basically the scheme. So what we did is that we generalized this into not just 4 blocks, n blocks, right? So we generalized it, and unfortunately, the asymptotic complexity is worse than other existing ORM schemes. So other existing ORM schemes would give you b times log n or log square n complexity. Actually, log square and log cube n complexity. Ours is much worse. Ours is square root n times something. But in terms of concrete cost, it still wins out. Right? I should have the graph. Why don't I have the graph? There we go. So if you do the comparison, so yeah, we did the measurements of 2 to the power 11 to 2 to the power 16. We did our own implementation of circuit ORM. This is actually done by the same author as circuit ORM. But anyway, our C-based implementation, because the previous one was Java. This one's faster by a factor of 2. And we see that this is the linear scan, circuit ORM, and our scheme. Okay? So yes, eventually circuit ORM does win out at 2 to the power 16. But it's still better for the smaller cases where you don't have to spend large initialization costs. And talking about initialization, this is just access. So in our case, this is all the cost there is. In circuit ORM case, you still have to do multiple write operations to actually initialize the data. You don't necessarily want that. And in fact, if you look at initialization, we sort of computed our own initial cost as the cost of shuffling, because that's all there is. But yeah, I mean, there is a fixed 100x gap between circuit ORM initialization and ours. Yes?
In the previous table, it looked like the circuit ORM was always better than the linear scan.
Yes, it kind of wins out. In our implementation, the break-even is somewhere here. So yes.
Which is better than the
Yes.
previous table.
Yes. Yeah.
Just because this is easier.
Yeah. Just the language difference. Yeah. Language difference plus the language difference also implies we can do various low-level things, such as ORMs always introduce round trips, right? Since they introduce round trips, we can do things like at the TCP level we can disable Nagel's algorithm. And that these are things that would aggregate. Let's say you're sending in 2 packets of data. TCP at the kernel level would aggregate these 2 packets and send them off to reduce bandwidth. The problem with that is that once you send 1 packet, it will wait for the next packet. And it will wait in the order of milliseconds. We can execute many gates in 1 millisecond, so that doesn't pay out. It actually helps to just disable that part.
Just make a week to find that.
Oh, you did too? Okay, great. We spent more than a week. Yeah, I feel like there should be a wiki of these tricks that we don't have to reinvent each time, but yes. So that's the bandwidth cost. If you want, we can talk a bit more about some of the things that we had to do to actually make this happen. So we already showed this. Okay, so sorry, I'm going a little bit out of order. But if you look at previous work, like I said, all implementations were tree-based ORMs. But there were, in the other cloud-based or not in MPCs, there were other kinds of ORMs. The hierarchical ORMs were already there. And the main difference between them is as follows. In the hierarchical ORMs, the initialization is pretty much as cheap as ours. So it's just a shuffle. That's all there is. However, each access requires a hash function to be computed by the client. In MPC setting, that would mean a hash function being computed inside a circuit. So that's a problem. So this is why all the implementations of ORMs use tree-based ORMs. They avoided that. What they paid for, it was in high initialization cost. So what we did in our case, if you think about our approach, is that we sort of merge them together. So we don't use the tree-based structure. Ours is kind of a hierarchical structure, except for it's limited to 2 levels. But at the same time, we don't use a hash function. we use the tree-based sort of nested relocation table kind of approach, where there's a nested ORM or a recursive ORM that will give us a map of which element goes where. Okay, so that's why we get the performance improvement. Yes.
So the protocol that you showed, where you just like, for example, mention random elements and shuffle, you see that it's like a hierarchical thing? Or
Yes, it kind of is, actually. So what happens is, so it's hard to see here, but what happens here is that this is sort of the first level of the hierarchy here. And once you keep using elements, these are the elements that end up in the stash. They get moved from the first level to a stash element, which is being linear scanned each time. So in some sense, this is a two-level hierarchy right here. But I sort of drew it in a different way. Yes. Kind of like, yes, it's a square root. So the title of the paper was Revisiting Square Root ORM. So yes, absolutely. So yeah, there were a few other challenges we had to fix, such as creating the position map itself. So if you think about it, you have a bunch of elements, you do the shuffle, and then we also have to create the position map, right? And the position map is essentially an inverse permutation, if you think about it. We have to know that if we're looking for position, if we're looking for element 0, we need the map to say element 0 is in position 2. So we'll have element 0 position 2, right? So this shuffle operation will also need to produce this. And for the first case, it's actually fairly easy, right? So you have some shuffle circuit that does lots of swap operations. What we do is that we sort of tag these with metadata 0, 1, 2, 3, 4 in sequence. We run them in reverse operation, in reverse side, with the same swaps. And so if this, so 0, 1, 2, so if 2 ends up there, we know 0 maps to position 2. And that's how we compute this column here. So that's fairly easy. The problem is that the next time around, you're doing some operation that gets composed with the previous permutation. So now, if that element goes here, that does not mean element 2 is mapped here. This reverse permutation doesn't get you there. So one way to solve this would be to use oblivious sorting. So we could tag them with 0, 1, 2, 3 again, and then sort them using these values, and that will give us the inverse permutation. But sorting again is n log squared n. That will add another log n factor to the complexity. We didn't want that. So what we did instead was come up with a new protocol that just inverses the permutation. So this is a secret permutation that we do not want to reveal, and we want to compute its inverse permutation. How do we do that? We actually use similar techniques in secret sharing and whatnot. It's not too novel. But the idea is that, so this is the permutation that we want to keep secret. The inverse of this is the output we want, pi. So how do we do it? The way we do it is that we have two parties, Alice and Bob. Alice locally generates a random permutation, pi a, feeds it in, uses that to permute this. This result is the composition now, pi a and pi inverse. This gets revealed to Bob. So Bob sees the original permutation shuffled in some manner that it doesn't know. So that's safe to reveal. Once we have that, Bob can locally compute the inverse permutation of that, get this. And finally, we have another permutation circuit. So pi a here and pi and inverse here. And since it's locally done, we can do the permutation and get just pi. So with two permutation networks, which is n log n instead of log squared n, we can compute the inverse permutation. So yeah, that's how we did the ORM. And we go, and the conclusion here, is we revisit a well-known scheme. As I said, it's an old scheme, not entirely new, but we showed that this actually can be instantiated with really low initialization cost, and the break-even point is as low as 4 elements. So the hope is this can now be widely adopted, and people can use ORMs in normal without worrying too much. Yes?
So in the militia setting, does the circuit have to check that it's the actual implementation?
Yeah. It has to check. It has to check that they are actually inverse of each other and whatnot. Yeah.
That's not too.
It shouldn't require sorting. No. I mean, the asymptotic complexity will be maintained. But yes, you'll have overheads. Yes.
So by this break-even point, you mean with the linear?
Yes, with the linear scan. I mean, at small sizes, that's pretty much the only thing you need to worry about. There is no other ORMs. Right. Yeah, that's it. I guess download, use, tell me how it is. If there are complaints, yell. Yeah.
Is your language similar to the Oblivious RAM stuff?
Yes, they were developed around the same time. Yes, it's more lightweight in the sense that it's a really thin pre-processing and it gets translated into C. So you can pretty much see what code is being generated. It's not too different from what you write. So the pros and cons is that Oblivion is a completely fresh start, right? It's clean slate. Yeah. They have their own language and they can design it however they want. In our case, we have a lot of C baggage to deal with. The good side is all the C libraries are pretty much available for you. You have dynamically sized array, it's a malloc. You have the simple things like networking. You have threads. Those are things I don't need to invent. Like you don't have to wait for me to implement that in the language that they're already there. In Oblivion, that's not the case. But yeah. Yes.
So those are things that you can use in the non-private part of the computation.
Mm-hmm.
Presumably, if you wanted to do something private,
I didn't get the question.
So you're talking about having all the power of C available.
Right.
That's in the sort of
both.
Not in the
No, both.
Okay.
Both. Even if you want to do private computation, but you want to split it up into 2 threads.
Okay.
That's okay. We'll need like a few 5-line wrappers around pthread, but anybody can write it. You don't have to change the compiler or anything. You can just have it. Yeah. There's almost nothing you need to do. Like the synchronizing primitives like mutex, the semaphores, like huge library of all these concurrency primitives that you don't need to reinvent. You should be able to just use whatever's already there with some wrappers, but that's something you can write. They don't require any modification. But yeah. And tools like existing tools, like profiling tools. See where your program is slow. The GCC profiling tools will work here. You have debugging tools. Valgrind will work on this. Valgrind was extremely useful here. So things like that does not have to reinvent it. So yeah. But yeah.